Okay, so hopefully at this point you've tried the Unit 4 Day 2 classwork. If you weren't in class with us and you have a bag of M&Ms or a bag of Skittles, I highly suggest doing this classwork as it's a good introduction to confidence intervals and what we'll be doing going forward. But if you have finished this activity, that's just kind of a good summarization of kind of what we're going to see coming in this unit. So if we go ahead and get out our notes for Unit 4, Day 2, we're going to start talking about summarize what confidence intervals are and kind of what we can do with them when we're talking about statistics. So on our Unit 4, Day 2 page, we'll start our notes at the top. It says the two major activities of inferential statistics are to use sample data to estimate values of a population parameter and to test hypotheses or claims made about a population parameter. So we're actually for Unit 4, we're going to focus on just the first part of this. And then for Unit 5, this is going to kind of be what we do in Unit 4. And then in Unit 5, we're going to do the second part, which is to test our hypothesis or claims. But for now, we're going to be looking at our hypothesis testing and estimating the values of a population parameter. So what that means is we're going to talk about a point estimate. A point estimate is a statistic that provides a reasonable guess about the population parameter. We're making an inference from a sample about the entire population. So we're trying to figure out information about an entire population given a sample. So point estimate, we use this p hat to represent our point estimate. And then X bar is the point estimate for mu. So this is all kind of going back to sample versus population. So over here, right, this p hat and our X bar, which just means mean, represent a sample. And excuse my lousy handwriting on this, but these represent a sample, you know what I mean? And then these two, would represent my entire population. So, and we're going to kind of use these in both cases when we're looking at percentages or proportions. And then if we're looking at mean and standard deviation, we'll look at these. But these estimate, right? The point is to estimate from a sample that we're given, estimate and make assumptions about the entire population given this sample. So we're never going to use a single value to do this, right? I'm never going to say, I know from my sample, I know that 50% of people like Starbucks from my sample. So I'm going to say 50% of the entire population does. That's not going to be very accurate. A single point is not a good idea. If we think about our normal distribution curve, right, we're trying to guess this value here, this middle value. It would be a lot easier, right, if we want to hit that target. Our goal when we're talking about our population is to figure out this value here, this value here about the entire population. Well, would it be easier to hit that if I was throwing a pencil at it or if I was throwing a ball? And if which one would be easier to hit that target, right? We would want a ball because a ball is bigger, right? Higher confidence, larger ball, bigger interval. So we want to be more confident that we're going to hit the target. So we're going to throw a ball, which in this case is going to be an interval. We're going to throw an interval to represent kind of where we think the middle of our sample or where the point estimate is for us. But we're never going to say that we're confident that this is the value. We're going to always put it in an interval form. We're confident that the actual population parameter lives somewhere within an interval. So what we're going to do is we're going to give a range of plausible values. So this is what we call a confidence interval. And what a confidence interval is, it's just your point estimate plus or minus your margin of error. And we're going to be able to solve for this with our calculator pretty soon. So a confidence level is the probability that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. When we talk about confidence intervals, we're going to have to use a percentage of confidence. The most typical ones that we use are 90, 95, and 99. We can really use any percentage that we want, but these seem to be the most common choices that we're going to choose from. Remember, the higher the confidence level we have, the larger our interval is going to be. Because if I'm going to say that I'm 99% confident that my answer is correct, I want my answer to kind of be a larger net of values to choose from. I don't want to say I'm 99% accurate and only give a couple of values to choose from. I'm going to kind of cast a wider net the more confident I want to be. And we'll see that when we look at some examples. So what a confidence interval does, right? If we're constructing confidence intervals, for example, let's say we were going to be 95% confident. So we took 25 samples from the same population and found these 95% confidence intervals. So this is the value that we're looking for here, right? This is the value. This is that population. Ooh, let me redo that. This is the population parameter that we're hoping to find, is this line here. So then every time we took a confidence interval, right, we said it was a range of numbers from here to here. And then we took another confidence interval and the range was from here to here. And what we want to find is that 95% of the samples that we take contain this value, this population parameter that we found. So if you look at all these samples, all 20 of them, only one of them did not contain my population parameter. If you can see this one here, did not. So if you think about 19 divided by 20, that would be a 95%. But what our confidence intervals are doing, they're creating a range of values. They're creating a range of values in which we believe that the population parameter lives somewhere in that range of values. So what we're going to do is we're going to calculate that range of values and say that we know with certainty, right, from our sample, we constructed this range of values and we're 95% confident that our population parameter lives inside of that. It might not be exactly in the middle. As you can see, some of these values, right, are kind of far off in terms of these were our sample means or our original point estimates. So they're not always exactly in the middle. However, the interval that we create does contain that population parameter. And that's our goal here, is that our range of values will somewhere have the accurate population parameter. So if we're going to run a confidence interval, there's a couple things that we need to be able to do. And one of the big things we're going to do at the end of every confidence interval is interpret our data. We have to be careful when we interpret our confidence intervals. There's really only one correct interpretation. Some people get kind of creative in how they interpret their confidence intervals, but it's pretty cut and dry, and we will pretty much use the same sentence structure every time when we're writing these out. So depending on what confidence interval you write, we're going to write, we're 95% confident that the interval from, and then the two values that you find, actually does contain the true value of the population proportion P. And this ending part will change a little bit to make the context of the problem, but we want to make sure that we're using the wording correctly, that our confidence interval is telling us how confident we are that our interval contains the population parameter. So if we were to select different sample sizes and construct many confidence intervals, 95 of them would contain the population proportion, kind of like we saw in our last slide. So we want to make sure that we're correctly interpreting our results every time when we solve for our confidence intervals. So how do we solve? There's some formulas that we can use. Luckily, our calculator does this for us, so we're not going to focus so much on the formulas, but we do have this formula here if we wanted to solve our confidence intervals. And this is provided on the test if you ever wanted to solve it by hand. One of the things that you we'll need to know is this Z value here is what we call a critical value. And that comes from, depending on which kind of confidence interval that you're solving for. So if you want to be 90% confident, you use the Z value 1.645. If you want to be 95% confident, 1.96. And that has to do with your normal curve and the value that falls on your normal curve when you solve that. So a 95% gives you a value here at 1.96, which represents the area under the curve for 95% confident. And like I said earlier, the interval for the confidence interval is really going to give us our point estimate plus or minus a margin of error. So once we are able to find a point estimate, we're going to then solve for a margin of error, which will add and subtract to that value to create our interval. There's a couple things we have to do every time we solve a confidence interval, and that is to make sure that our conditions for running a confidence interval are met. So we can't just run a confidence interval anytime we want. We have to make sure that the sample was set up properly to run a confidence interval. If the sample was not set up properly, then you're not going to get data that will help you find your population parameter. And that's our goal here, right? If I don't take a simple random sample, if I just did a convenient sample, then my sampling method is off, which means that my data is also going to be off. So we are always going to, every single time, check these three conditions before we run our sample. So the first one is that our data comes from a simple random sample. The second one is that our n times p-value is greater than or equal to 10, and our n times 1 minus p-value is greater than or equal to 10. That just means that we asked enough people for this sample to be valid. Too small of a sample size is not going to give us accurate information. And then the last one is that our n value is less than 10% of our population. What this really means is we're checking for independence. We want to make sure that our n values are independent of each other, so that we want to make sure our n size is reasonable. And when we go over examples, these might make more sense. So again, we can use these formulas, but nice enough for us, our calculator solves confidence intervals for us. And when we look at examples, I'll show you kind of how we're going to use these buttons to go ahead and solve. Okay, so let's go ahead and look at our notes, and I'm going to switch screens. That way you're looking at on the paper. Okay, so these were the notes that we had that we just took and talked about. So if I turn my paper over, we have some examples that we're going to look at. So a Pew Research Center poll of 101,501 randomly selected U.S. adults showed that 70% of the respondents believe in global warming. So to run a one prop Z interval is what we call it, a one proportion Z interval. There's some information that we need. We're going to need an N value, which is your total amount of people that you're asking. So in this case, that would be 1,501. Then you're looking for the percent or the proportion of people that responded to this in whatever way you want them to respond. So in this case, we have that 70% of respondents believe in global warming. So that means my p-value, my proportion here is 0.7. We'll also need our X value. X is, instead of the percent of people that responded, the proportion of people that responded. So you can find X by just doing N times P. So in this case, if I do 1,501 times 0.7, I would end up with 1,050.7, which will just round up to 1,051. So these, and then we need to know how confident that we want to be. So in this one, it's asking us to construct a 95% confidence interval. So we're going to be 95% confident. And truly, in all of our confidence interval questions, we're going to do the exact same thing over and over and over again. So we kind of find the variables or the values that we need. That's this stuff over here. We're going to check our conditions, and then we're going to run our confidence interval and interpret that. So first we figure out what variables we need. Now we need to check those 3 conditions that are on the front. So again, these were on the front page. But I need to make sure that it comes from a simple random sample. So it says randomly selected US adults, so that is a simple random sample. Then we want to make sure that our condition 2 is that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Well, you just did n times p over here and got 1,051. So that's definitely greater than or equal to 10. So now if I do n times 1 minus p, so if I do 1,501 times 1 minus 0.7, I end up with 450. That is definitely greater than or equal to 10. So that condition is met as well. And then our last condition is that our n size is a reasonable n size for our population. So what I do in this problem is I just take my n value and I add a 0 to it. I then ask myself, is it reasonable to assume that there are 15,000 adults that could have been in this study? Yes, there's definitely more than 15,000 adults in the US that I could have asked to be a part of this study. So we can go ahead and check that off. Okay, so we have the variables that we need. We checked our conditions. So now we're going to go ahead and run a 95% confidence interval. So on my calculator, I'm going to hit stat, go over to test, hit stat, go over to test, and then I'm looking for one prop z interval, one proportion z interval. So I believe we have got to go down to letter A. So now it's going to ask for this information, which are the values that we already found over here, right? Our x value, which was n times p. And this doesn't like decimals, so we're going to round this up to 1051. This running a confidence interval, it does not like decimals for x. So we'll just round it up. Our n value was 1501. And then we want to be 95% confident. So we type that information into our calculator and then hit calculate. And our calculator will do the work. Right up there is that confidence interval that we need. So the interval here is 0.67702 to 0.72338. All right, so then we're going to interpret this interval. Like I said, we're going to interpret all of our intervals basically exactly the same. The structure is going to be pretty much the same for every interval, for every confidence interval that we interpret. So we're going to put I am, and then whatever percentage we did, 95% confident that the interval, and we state the numbers that we found. So 0.67702 to 0.72338 contains, and then whatever our word problem is discussing. So 70% of respondents believed in global warming contains the true proportion of US adults who believe in global warming. I ran out of room. This is a critical part. Interpreting our results is the most important part of this. We can't be skimpy. We can't try to paraphrase this or write as little amount as possible, because this is the results from our statistical study. We don't want to give out inaccurate information or not give enough information to people just because we're being too lazy to write out our full sentence. So we want to make sure that our interpretation involves our interval, the confidence level that we have, and then what the problem is pertaining to, so that someone doesn't have to go back to the beginning to read this and understand what we're talking about. So this is a very important piece, and on your test and quizzes, it is worth a lot of points that you interpret this correctly. So make sure that you're spending the time to do it now. All right, so let's go over another example similar to the one that we just did. So in the United States, approximately 900 people die bicycle accidents each year. One study examined the records of 1,711 bicyclists aged 15 or older who were fatally injured in a bike accident and had been tested for alcohol. Of these, 542 tested positive for alcohol. So we're looking at just the study, right? We're not talking, even though 900 people die, that's not part of our study. Our study examined the records of 1,011 bicyclists. So when we talk about our variables, N is going to be 1,711. And then of these people, 542 of them tested positive for alcohol. So that is not our percent, that's our X value, right? Our X here is 542. If I want to find P, right here, to find X, we did N times P. If I want to find P, I would divide X by N to get P by itself. So I could do X divided by N if I was looking for my proportion. So you've got to be careful knowing the difference. Are you given the percent or are you given an X value? You can always solve for the other one that you're missing by using one of these two equations. It's the same equation, just manipulated different ways. So if I go ahead and do 542 divided by 1,711, I get that my point estimate or my proportion is 0.317. So, and then for my confidence interval, it says I want to be 99% confident. So this is the variables that we need to be able to run our confidence interval. So then the next part we're going to do is check those same conditions that we checked last time. So first we're looking for a simple random sample. Since we're running a study, it's pretty easy to assume that our study was run with a simple random sample. That is statistically the best way to run a study. So we're going to assume that this is a simple random sample. Then we're going to test that our N times P value is greater than or equal to 10, and our N times 1 minus P value is greater than or equal to 10. Remember, N times P is just X, so you don't really have to solve for this. You already know it's 542, but if you wanted to, 1,711 times P, which is 0.317, gives me 542. Again, we'll just round it. And then N, this should be N, sorry, N times 1 minus P, so 1,711 times 1 minus 0.317 gives me 1,169, really, which is also greater than or equal to 10. So our condition in sample size is met there. And then our last condition is just to check that our sample size is a reasonable amount. So if I take my N value and I add a 0 to it, if we're studying the records of bicyclists, it is safe to assume that there have been more than 17,000 bicycle accidents for people between the ages of 15 and older. So we can assume that this is a good enough sample size, or that sample size is reasonable. We check the same three conditions every single time. This is also an important step in the process. We can't just skip over this because, hypothetically, if one of these conditions weren't met, we should not run a confidence interval. For the majority of the problems in our class, we're going to assume all of our conditions are met, so we can run the confidence interval, but we never want to say we're sure they're fine and move on without doing this piece of the puzzle. Okay, so now let's go ahead and run our confidence interval. So again, to do that, we hit stat, go over to test, down to 1 prop z interval. Our x value is 542. Our n value is 1,711. And I want to be 99% confident this time. So I just took this information that I have here and I put it into my calculator and I hit calculate. So I get that my interval is 0.2878 to 0.34574. So now we'll go ahead and interpret this interval. Again, very similar to how we did the last one. I am, in this case, 99% confident that the interval contains the true proportion of bicycle accidents where alcohol was involved. And again, you can change the wording of this part a little bit to summarize the problem, but it should involve the context of what we're solving. Okay, so that's just 2 examples. We're going to do a lot more. So if you're not feeling 100% about it, I promise in the next couple days, we're going to be running confidence intervals over and over and over again. So you'll get there. The last piece to this is just if we want to find the sample size that we need in order to have the confidence interval that we're looking for. So for instance, I have information and I want to know how many people would I need to ask to confirm this information or to figure out what my population parameter is. So we're actually solving for the n value or for the sample size. So to do this, there are 2 equations. These 2 equations will be on your test. So you're not required to memorize them, but you are required to know how to use them. So these are our 2 equations. And the difference to us is just if there is a point estimate or not. If I know a point estimate, if I have a rough idea of what I think the percentage is, then I'm going to use this equation. If I don't, then I'm going to use this equation. So this is to find our n value or the sample size that's needed in order to be as confident as we want to be. So let's look at an example. So it says the internet is affecting us all in different ways. So there are many reasons for estimating the proportion of adults who use it. Assume that the manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So this is kind of the information that we need. So it says in 2006, 73% of adults use the internet. So this would be, right, that our population parameter or that our proportion here is 0.73. So for part A, we're going to use this equation because we have an estimate already that we're going to base this off of. So if I want to do part A first, I'm going to use this equation, z star squared times p times q over e squared. So z star is that critical value we talked about earlier. And we have a table of that in our notes that we can refer to. If I want to be 95% confident, I'm going to use the critical value 1.96. So this is going to be 1.96 squared. P is 0.73. We should remember at this point, we talked about this a lot in Unit 3, that Q, right? Q is 1 minus P. So if P is 0.73, that means Q is 0.27. Because these should add up to 1. And then our margin of error, we want to be within 3 percentage points. So my margin of error, 3% is 0.03, right? If I turn this into a decimal, is 0.03 squared. So then I'm just going to type this into my calculator so that I can solve. So I'm going to do 1.96 squared times 0.73 times 0.27, and then I'm going to divide that by 0.03 squared. And I get 841.31. Now, remember, I'm trying to survey, I'm looking for a sample size. I'm looking for the amount of people that I need to ask. So I cannot ask 841 people, 41.3 people, right? There's no way to ask 0.3 of a person. And asking 841 is not enough. So I always have to round this value up so that I have enough data to be accurate. So I'm going to ask 842 adults to make sure my sample size is large enough to be 95% confident. Okay, so the only difference in part B is that we're not given a point estimate to start with. So then we just use this equation. It's basically built the same. The only thing is that instead of P and Q, we just use 0.25 in their place. So when I solve this, I'm just using N equals the critical value squared times 0.25 over E squared. So my critical value stays the same because I'm still doing 95%. So I'm still at 1.96 squared times 0.25. And then my E value is still, right, I want to be within 3 percentage points, so 0.03 squared. So the only thing that changed here is just because we don't know P, we also don't know Q, so we just put 0.25 in its place. So I'm going to do 1.96 squared times 0.25 divided by 0.03 squared, and I end up with 1,607.1. So I need to ask 1,068 adults. I had 1,067.1. So I've got to round that up to 1,068. This number is always going to be bigger because we don't have any starting point to go off of. Right here we had an estimate that we were going to start with, so we were just building from that. This we're starting from scratch, so we're going to have to ask more people in order to be as accurate as we want to be. So those are our notes on confidence interval, kind of just an introduction before we keep practicing this throughout the week.